Hey guys, welcome back to my CCNA 200-301 course. Patrice is here, and in this video we are going to review OSPF Basics together. Are you ready? Let's get started. First of all, I have to mention that when I say OSPF in this video, I mean OSPF version 2, which is being designed for IP version 4 routing. OSPF has another version as well, OSPF version 3. And that version is being developed for routing for IP version 6. It used to be in Cisco CCNA certification exam topics, but Cisco removed it. So you don't need to know about it for CCNA exam, but if you are interested in, you can search it up, OSPF version 3, and learn about it. When you configure OSPF for the first time, OSPF process kicks in, and there are three main stages for OSPF process. The first one is forming neighborship with other routers that have OSPF configured as well. Once that neighborship is formed, the routers start to exchange the information or exchange their database. And finally, once all routers know about all available subnets and available routes for them, then they start to calculate the best route and install that route in the routing table. Now let's go through each of these steps one by one. First, neighborship formation. When you configure OSPF on a router, it starts to send messages that are called hello messages. And it's exactly just like a hello because it wants to start conversation with other OSPF neighboring routers. So if a router receives this hello message, it says, okay, hello, I'm here too. I want to talk to you with OSPF. And they check some parameters together, like their area ID, which I'll be talking about it in the next few slides. And then hello interval, which is the interval of hello messages, and dead interval, which is the timer that routers calculate to see if the neighboring router is still alive or not, and other parameters. And if they agree on those parameters, this neighborship actually forms. And this neighborship has different states based on this conversation and the ones in the next slide. And these states are very important for OSPF troubleshooting. When they start the conversation, the state or the status goes to init, which means initialize. So they initializing this neighborship. And once they started the conversation and they agreed upon the parameters, the state goes to two-way. Two-way means that they agreed on the parameters and they are ready to exchange the information. So this is the first initial steps that are required. If they do not agree on the parameters, this neighborship won't form. There are different parameters in these hello messages. One of them is router ID, which is the identity of your router within the OSPF infrastructure. Router ID is just like an IP address. It's a 32-bit address, and you can configure it just like an IP address, but this is not an IP address. It's just an identity of your router in the OSPF infrastructure. There are some options to configure this or let the router pick the router ID. First of all, you as the administrator can configure the router ID on your router, which I'll show you in the next video. If you don't do that, router will pick the highest loopback IP address and select it as the router ID as well. So if it has multiple loopback addresses, it picks the biggest one or the highest one. And if you don't have any loopback interface on your router, it checks the all online or the interfaces that are in up status, and again pick the highest one or the biggest IP address and select it as the router ID. So router ID is an optional configuration. If you don't set it, router will find something for itself. And in the OSPF packets, at the protocol type, the protocol type is 89. I'll show you in the next slide. And OSPF, especially when it starts the conversation, and the destination IP address of all hello messages is 224.0.0.5, which is a reserved IP address for all OSPF routers. So it actually multicast this message to make sure that all neighboring routers, if there is multiple routers in the neighborhood, and they all will receive this message and they will react accordingly. But for some packets also, OSPF uses the unicast addresses as well. I'll show you in the packet capture in the next slide. The next stage is database exchange. As I mentioned in the previous video, OSPF is a link state routing protocol. And you'll hear a lot of abbreviations that start with LS, which stands for link state. The first one is LSDB. The OSPF database is called LSDB, or link state database. Once the neighborship forms, it is in two-way and routers are ready to exchange their information, the first information they exchange is their DB description. And in this stage, the neighborship state goes to XStart, which means exchange start, and then the exchange. And once that description conversation finished, they're ready to send the detailed information, because that database cannot be sent at once. So it has to go gradually through LSAs, or link state advertisements. And what has been sent through LSAs? It is called LSU, or link state updates. And in this stage, the neighborship state goes to loading. And once all information exchanged between the routers and everything is finished and they know whatever they need to know, the neighborship state goes to full. In the next video, I'll show you when you check the OSPF neighborship, if it is in full, that means everything is okay in terms of neighborship state. I configured two routers with OSPF and captured the traffic between the two routers, and here is the summary. As you can see here, the first router that has been configured with OSPF IP address was 192.168.1.1, and the destination IP address is 224.0.0.5. That is the multicast address that has been reserved for OSPF, as I mentioned before. And here you can see the protocol type is OSPF and the number is 89. And destination address field is here. And if we open OSPF header, we can see a lot of information here. The first one is, this is the hello packet, because it actually the start of the conversation. And my router ID is 1.1.1.1, and the authentication type is null, which means that authentication is not being configured on the OSPF in this router. And in the hello message information, you can see the data like hello interval, which is 10 seconds by default, or dead interval, which is 40 seconds by default again, and other information. Once I configured the OSPF on the other router as well, you can see that the other one, 192.168.1.2, also started to send hello messages to the multicast address. And once they knew each other, they started the conversation with unicast addresses. So OSPF basically uses both unicast and multicast. Sometimes depends on the packet, or sometimes depends on the situation. Anyway, it uses both, but the initial hello messages always goes to 224.0.0.5, so router can make sure that all neighboring routers, if there is more than one, will hear that message. And once that conversation happened and the state went to true away, you can see that the next message is a DB description. And the message type here is DB description. And as you can see in the OSPF header, the router always sends its router ID. So router ID is always in the OSPF messages. And once the database description exchange and they know about the information they need to exchange, now the LSR starts. LSR stands for link state request. So it is the start of sending the LSUs. So router 2, actually 1.2, started to ask for updates. Send me the LSAs. And that moment, router 1 started to send the LS updates. And since I didn't have much networks or subnets to be exchanged between the two routers, you can see there's no much updates. But if you have a long list of networks that needs to be advertised, this is going to be more than that. And then ls acknowledge, and that's it. So you saw that all the stages we talked about. First hello, and then once they agreed on the parameters, DB description, and once DB description happened, then they started to send the ls updates and know about what they need to know. Now it's the time to select the best route. OSPF uses an algorithm called Dijkstra, which is coming from the name of the inventor of this algorithm. And based on this algorithm, the cost of each link is calculated, and at the end they all sum up together and then compares, and the one that has the lowest cost will be picked as the best route and will be installed in the routing table. This cost is calculated based on a formula, and that formula is reference bandwidth divided by the bandwidth of the interface. By default, that reference bandwidth is 100 million, which is 100 million bits, and basically it's been designed for 100 megabits per second interfaces. So if you have interfaces bigger than 100 megabits per second, I would recommend you to make some changes. Actually, you can change all of these individual items in the formula. First of all, you can manually select or set the cost of each interface. And in that sense, OSPF will not do the calculation and will be using the cost that you configured on the interface. You can also change that reference bandwidth, or you can change the bandwidth of the interface. So all of these three items are possible to manipulate, and you need to change it accordingly based on your network design. Now let's talk about DR and BDR concept. DR stands for designated router, and BDR stands for backup designated router. When you have multiple OSPF routers in a network segment, like this you can see in the slide, how OSPF works is it doesn't flood all information between all the routers. In these circumstances, one of the routers becomes the master or designated router. How it's been picked? The router which has the highest router ID will be picked as the designated router. Let's assume that this is the designated router now. And what would happen is all other routers will send their updates to this designated router, and this is the designated router's responsibility to send all other routers to all other routers information. So we don't have a mesh conversation between the routers. Everyone sends their data to the designated router, and designated router will send the data to the others. Okay? And since this role is very important in these circumstances, we need a backup as well. So the router with the second highest router ID will be picked up as the BDR, or backup designated router. So if the designated router fails, the backup designated router will take the responsibility. The final topic is area. Area is basically the perimeter that OSPF routers will do whatever we talked about. All of those neighborship formation, database exchange, LSA conversation, if any changes happen to the network, etc. When you're dealing with a large number of OSPF routers, these conversations may bring some delay. So in these circumstances, you may need to separate your routers to reduce the number of these flawed and other things that we talked about. So this brings agility and reduce that delay that may happen because of the numerous number of OSPF routers in your network. So we divide our routers into different areas. So the routers within each area will talk to each other, and if any changes happen, they will let the others know, and all of those things we talked about. If you're dealing with multi-area design, area 0 is there, and it has to be there because this area 0 is called backbone area, and the communications between the areas will be happening through backbone area. I mean, area 1 and 2 in this scenario cannot talk to each other directly and has to advertise their network and all of those things through backbone area. So backbone area is a kind of a master or a replicator between the messages. So each area needs to have at least one connection or one router with a single interface, at least, to the backbone area. And this router will be called ABR, or Area Border Router, and it is responsible to advertise the routes of its own area to the others, I mean to the backbone area, and backbone area will send it to the other areas, and also receive the updates from area 0. So in this situation, if, for example, a link between this router and that router goes down, other routers do not need to know about it because their communication will be happening through the area 0, and this reduces the number of messages that is going through OSPF. Some other terminologies, and the routers inside the area 0 are called backbone routers. So these routers are backbone routers. Other routers are called internal routers. So the routers that are in a non-backbone area are called internal routers. The routes that are exchanged internally within the area are called intra-area routes, and the routes that are exchanged between the areas is called or are called inter-area routes. Also, for example, as we mentioned before, this is your network and this is managed by you. So this all infrastructure is one AS, and that AS is managed by you. Let's assume that your company merges with one other company, and that company also has OSPF infrastructure, and now you want to connect these two companies together through OSPF. In these circumstances, one thing we can do is putting one router at the edge of our AS to do all of those things we talked about ABR, but this time for the whole AS, and advertise the whole AS to the other AS and receive the information from other AS. And this router is called ASBR, Autonomous System Border Router, and this will allow you to communicate to different AS through OSPF. Alright guys, this was our today's video. In the next video, we'll be configuring OSPF. I wish you enjoyed today's video and see you in the next ones.